In this video, we'll derive the gradients of the loss function with respect to the different hidden layers in the neural network. So now we are again pushing forward with getting an expression for the parameter gradients so that we can put those into the description of the stochastic gradient descent algorithm applied for neural networks. All right, so we looked at the gradients with respect to the output of the neural network, and then we looked at the pre-activation and at the output layer. And so we could continue like this, deriving it for any other hidden layer. But if we were to do this every time by hand, like we've done so far, this might get a little bit complicated. So can we sort of take a step back and try to see how, instead of looking at individual neurons and then computing what's the actual gradient or partial derivative, and then putting those back into gradients, can we get a more general formulation for the other hidden layers, the other layers in the neural network? So what we can do is actually use the chain rule to get a more general formulation for the gradient with respect to any hidden layer. And then from that, we'll be able to derive a procedure for computing the gradients for all hidden layers. So we know that from the chain rule that if we have a function p of a, which depends on a, and if this function is such that it can be rewritten as a function of intermediate results, which we'll call qi of a, and so where I indexes the intermediate results, then from the chain rule we know that the partial derivative of p of a with respect to a is just the sum over all partial results of the partial derivative of p of a with respect to the ith partial result times the partial derivative of qi of a with respect to a. So for instance, in the neural network, if we wanted the derivative with respect to the activation of this neuron, well, then we would need to consider, and then we could use, say, the pre-activation gradient here and here as the partial result. Because if we have this, then we can compute the loss function. So what chain rule would tell us is that to get the partial derivative for the activation here, we would need to combine we need to take a sum over all paths between what we're making a partial derivative over and what we want the partial with respect to what we want our partial derivative. So in particular, we would have to add the product of the partial derivative of our loss function with respect to the pre-activation, so sort of this part of the path, times the partial derivative of the pre-activation at the output layer with respect to this, so that's this part of the path, plus the other components in the other path between the activation here and the output. So that would be the partial derivative of the loss with respect to the pre-activation times the partial derivative of the pre-activation with respect to the activation here. Okay, so we can invoke this chain rule and use it in computing our gradients by using for the activation of a unit in some layer. The partial or intermediate results would be the pre-activation in the layer above for all the for each ith layer unit in the layer above, and then p of a would be our function would be the loss function. Okay, so that's what we'll use to derive the gradients with respect to the hidden layers. All right, so if we are at the kth hidden layer, and I want the partial derivative of the loss with respect to the gth activation of the gth hidden unit for the kth hidden layer, well, the chain rule tells me that if I want to use as the intermediate result the pre-activation A at the k plus 1th hidden layer, so that's the hidden layer above, well, I need to sum over all of the pre-activation at the layer above. I need to multiply the partial derivative of the loss with respect to that pre-activation, and then multiply that by the partial derivative of that pre-activation, the ith pre-activation at the layer above, with respect to the activation at the kth layer with respect to the gth hidden unit, which is the thing we want to get our partial derivative with respect to what we want our partial derivative. So, so for instance, if we're here, we're summing over this path and this path. Or if we were at this hidden layer, then we'd need to take into account the gradient that comes from this partial, this pre-activation, and then this pre-activation, and this pre-activation, and so on. Let's remove some ink. Okay, so let's assume that we've already computed that before. And so, for instance, if we started at the output layer, we could assume that we've already computed the pre-activation gradient at the output layer. Now, the part of this expression that we don't know yet is this part here. What's the partial derivative of the pre-activation at the layer above with respect to the activation at the layer below for the jth unit? Well, let's remind ourselves the formula for the pre-activation at a given layer. So, so this is k here, and I have k minus 1 here. So this could instead be k plus 1, and then I would have just k here, and k plus 1 here, and k plus 1 here. So for the IF unit at the layer above, its computation is just a linear transformation, so a bias plus a linear combination of all the activation of the units in the layer below. So all the jth unit in the layer below. So if I want the partial derivative of that expression with respect to a specific hidden unit, so for that specific hidden unit, all the other terms except the one for the actual value of j I'm interested in, the partial derivatives would be 0. And so for the case where this j is the same j as this one here, then I'd have a constant times the actual activation of the unit, and the partial derivative of that would just be the scalar. It would just be wkij. So this term here is simply equal to the connection between the jth neuron in the hidden layer k and the ith neuron in the hidden layer above. Okay. Again, let's remove some ink. So now this expression corresponds to, we can think of it as taking the vector of gradients with respect to the pre-activation at the layer k plus 1 multiplied by the column of that matrix. And so it's multiplied by the column, the product of the vector here with the vector corresponding to the jth column, and that's because we're summing over the row index. So then we'd be going from the first row, second row, and so on. So we're taking the product of these terms along the column, the jth column of that matrix. And so we can write it in this way. We can say, I'll take the jth column of matrix W, and sorry, there should be a k plus 1 here. So I get the and sorry, this should be dot, and this should be j here. So dot means I'm taking all the elements for the row index, and j here means that I'm taking the jth element, the jth column. So I take the jth column of that matrix, and so that would be a column vector. So I take the transpose to make it into a row vector, and then I can multiply that by my gradient with respect to the pre-activation. And so this would be exactly equivalent to that. Now, if I want the gradient, so if I want the vector partial derivatives for all activations in the hidden layer k, then all I can do is I take my whole matrix, I transpose it, and then I multiply that by the vector of gradients for the pre-activation at the hidden layer k plus 1. And that's because the definition of multiplying a vector by a matrix is just multiplying that vector with all the rows of that matrix. And so if we go back at this formula here, so here we had a dot, and here we had a j. And so by taking the transpose, it means that we're multiplying by this row vector, and this row vector would correspond to the jth row vector of the transpose of that matrix. Okay, so that's one way of taking our partial derivatives and then converting that into a vector partial derivative, so of the gradient, we simply take the partial derivatives of, the gradient of the pre-activation at the layer above, and then we're multiplying by the transpose of the connections between these two adjacent layers. And now if we want the gradient with respect to the pre-activation at a given layer, so if you want the partial derivative of for the hidden layer k of the gth pre-activation with respect to our loss function, well, again, I can use the chain rule. Now in this case, I could compute it as the product of the partial derivative of the loss with respect to the jth activation in layer k times the partial derivative of the hidden layer k jth activation with respect to the jth pre-activation of hidden layer k. So in this case, I don't have a sum, and that's because I compute, as I see here, the jth activation in a layer does not depend on the pre-activation of the other units in that layer. It's just a nonlinear function, the activation function, applied on the jth pre-activation of the pre-activation vector. So in this case, this only depends on the jth pre-activation. And now, so for this term, this is simply the partial derivative of my activation function evaluated at the value of the pre-activation. Okay, so this would be simply the gradient or the derivative of my chosen activation function. Now, if I want to compute the gradient of the loss function with respect to my pre-activation, so the vector of partial derivatives, what I have to do is to take all the partial derivatives and put them in a vector. Now, remember that it only corresponded to taking the partial derivative of the loss function with respect to the activation of a neuron and multiplying it by the gradient or the derivative of the activation evaluated at the pre-activation of that same neuron. So we can just achieve that by taking the vector, so the gradient of the loss with respect to the activations and multiplying that element-wise, doing an element-wise multiplication with a vector that contains all of these gradients of the activation function for all neurons. Neurons 1, 2, up to j, and then up to the number of neurons in that layer. Now, those who are familiar with vector calculus, they might have taken this step, just taking the, and that's, you can think of this as the vector version of the chain rule. You take the gradient with respect to all your partial results, and then you multiply that by the gradient of the partial results with respect, or the intermediate results, with respect to the, in our case, the pre-activation. And now I just want to mention that this expression here is called a Jacobian. It contains the gradient, the partial derivative of all elements of that vector with respect to all elements of that vector. So the partial derivatives of all activation in the hidden layer with respect to all pre-activation. And it turns out in this case that this Jacobian is actually a diagonal matrix. So all off-diagonal elements are 0, and that's because the activation for a neuron only depends on its pre-activation. It doesn't depend on the pre-activations of the other neurons, so the partial derivatives would be 0. And also talk about that to justify why I didn't use that notation to mean that vector. So if I remove some ink, I actually wrote, sort of use a bit strange notation by saying I'm going to construct a vector where all elements is the derivative of the activation function. And that's because this here is not equal to that. But doing the vector product of this with that matrix actually in this case corresponds to taking that matrix and doing an element-wise multiplication with that vector, and doing an element-wise multiplication with that vector, the vector of derivatives for all the activation functions evaluated at all the pre-activation values. All right, so this is how we compute the loss gradient with respect to hidden layers, both at the activation and pre-activation level.